just, it's not necessarily associated. It's not, wholly an Archain thing, right? This is lots of different people working on this. So we're setting up, and we're copying over the videos that we've recorded so far into the Casper channel, and then we'll talk about, branding and that sort of thing after the fact. But we're just getting the ball rolling so that it's, essentially Casper is kind of its own community, and should have its own channels. So we've got that underway. Certainly Archain will lend its logo and support to the channel, and whoever else wants to can do that as well. So I will go ahead and get started. I know Vlad has some interesting updates, and Carl has some interesting updates, at least based on our chats, Vlad. That's what I heard. Can you hear us now? Rick, can you hear us?
Well, I can hear you, Greg. Yeah. Okay, good.
I can hear you guys just fine.
Okay, sweet.
Okay, yeah. So I just joined via my phone for audio, but I'm keeping my my laptop open as well.
Okay, cool, awesome.
I couldn't hear you on there, but I'm going to use it for screen sharing later.
Okay, awesome. That's really awesome. So I'll just give a quick update on my end. So I now have an if and only if proof on the trace. So if you have a trace, then you have consensus. If you have consensus, then you have a trace. And in a category, in a trace monoidal category, where the morphisms are smart contracts, as row calculus programs, and the types are the types that are generated from the ladle algorithm. So that's and it's interesting because if you go through the proof, it's in one direction. So from trace to consensus, it's not constructive, at least in the sense that you can achieve consensus, but it doesn't necessarily tell you how that's done. It's just that you have enough data to form a consensus. So that's very nice from my point of view, because it gives us an equational characterization of what safety is. So we don't, as long as the consensus algorithm does satisfies the trace conditions, then we know that that it will do the job. It will provide consensus. The other thing I've been thinking about is expanding out to the binary, from the binary case to the n-ary case. And based on my initial calculations, I don't see that there's a problem with that at all. So that's also a smooth extension. And then the other thing I've been thinking about is how to think about your ideal adversary calculation in terms of the trace. So how do I?
Cool.
Yeah, how do I show that the ideal adversary calculation satisfies the trace?
The ideal adversary for the network attack can be, it's quite easy to understand what he does. He just basically gets to choose the order of message propagation. So if you can show that there is no order such that the estimate changes, then that's they're doing the same thing that the ideal adversary does so safety calculation basically is if ideal adversary fails, then return false or true, depending on whether you're unsafe or safe. And then otherwise return the opposite.
Cool. Yeah. Okay, that makes sense. I mean, essentially, in the trace arguments, this comes down to there are only two cases that I have to consider when we're looking at smart contracts that are row calculus programs. And both cases have to do with because there are only two cases for race conditions. And and there's a transform on row calculus programs so that all race conditions can be converted into message arrival order.
That's really good,
So I think we can bridge that gap fairly easily then.
So basically a message arrival order, but you don't need to order all messages, right? Only some of them, right?
That's correct. Yeah.
So can you like inspect the row calculus term and identify exactly which consensus decisions need to take place?
Yes,
say?
You absolutely can.
And how does that relate to transactions?
So a transaction is exactly when you have made a decision on which input meets which output.
That sounds like so. But what if you have like a race condition?
Right. So the race is decided in a transaction.
Okay. This is interesting. Okay. So you're telling me that like external transactions will basically like pick reductions when there's race conditions.
That's correct.
And like that's all they do. So like
you basically need a
way to like you basically need to address a way to address reductions and then like call transactions.
That's it. That's it exactly.
That's interesting and weird.
Well, I mean, it's like, I mean, the nice thing is that it doesn't pick. It's just that everyone has to consent as to what the choice is, right? So the transaction is only committed if you have consensus on what the choice within the race is. Who's the winner of the race? That's what the transaction constitutes.
Right. That's interesting. Yeah. So have you thought about how you would implement, say, a basic currency on there? Like, with the kind of access control to the fact that like, I don't want anyone to be able to send my balance to any account.
Yeah. I mean, that part of the puzzle is standard, right? There's nothing different there. Right?
I guess you just implement it in some like higher level language that compiles down to like the row calculus.
That's exactly it, and that's what row lang is.
But then you need to have like some wallet that understands how to look at that high level language and understand which.
Absolutely, and actually, all of that's already been written up. So we've written up like 3 different kinds of wallets, and now we're writing a tutorial on the basic wallet and the security of the wallet and all of that. So that document is also underway.
Cool. Yeah. Sweet. Quality update.
Yeah. So I hear from you that you and Carl were optimizing Casper and have some nice results there. Yeah.
So basically, we've been kind of working through the bottlenecks one at a time for a few weeks now. And we finally got basically all of the bottlenecks that affect the specification out, at least like the major ones. There's like still one bottleneck about like the way we're doing memory management in Python, but it's not, I wouldn't say that like it's going to affect the spec. So basically, what ended up happening is we went from this kind of like very kind of functional mathematical kind of definition based approach to one where we're using kind of like state on the validator in order to minimize the amount of recomputing that needs to happen in order to provide the inputs as necessary to like do that the same calculation, but basically just like more efficiently rather than recompute stuff. We keep dictionaries around and update them after we observe bets, and then basically pass the relevant information down. So basically, the way there's a kind of nesting where like a validator has model has an adversary that they initialize when they run a safety calculation, which in turn has model validators, which it uses to try to change the estimate. We used to be doing a lot of the work in the model validators, and that was like less efficient because there's way more of them. And now we kind of do the work in the validator and pass down the relevant arguments through the kind of chain of adversary to model validators. So I think that it's a little bit better organized now. And like, I think the only exponential factor left is this mem copy that we're doing some deep copies out of paranoia. I mean, you just kind of like turn that into regular copies as necessary, which should be possible. It's just a matter of like making sure not to mutate certain things, or to like when you mutate them, know that you're doing that, so that things don't change under your,
Yeah, that seems like a kind of deep in the weeds Python thing. If you're just trying to prove the theory, I would just keep doing deep copies unless you're trying to. I mean, why would you be making performance tests on Python?
Yeah, no, completely agreed. Like all the other stuff, like, and that's the reason why I kind of like, this is not super duper high priority for me to like go through this and figure out this copy stuff. But like all the other changes were they affect the specification, right? Rather than compute things in like that like a naive way that is just derived like simply from the definition by like kind of brute force. Have like a kind of more clever algorithms for doing it.
Yeah, I mean,
another thing that's sorry.
I would just argue that you actually probably want to keep the deep copies because that improves your ability to determine correctness, right? I mean, you should take the performance hit in Python just so you know that you're moving the right objects around.
I see what you mean.
The one thing along those lines, as you do these transforms from the mathematical definition to an implementation, I mean, it sounds like essentially what you're doing is memoizing state or getting more efficient characterizations of state, and there monadic structuring is going to be your best friend. Because when you structure it as a monad, then you just have some laws about how you're managing the state, and those are the monad laws. And then how it's implemented on the back end, as long as the implementation itself is correct, it's packaged up nicely as a monad, and you're done. So that helps.
That's really cool. And what would monad laws look like? Would they enforce invariance?
They do enforce invariance. The most important, are kind of the three the three stooges, right? Shape, wrap, and roll. So you've got the container, which is the thing that's packaging up your state. You've got how you put stuff into the container. That's wrap. And you've got how you flatten nested containers. That's roll. And that it's the same three stooges, whether you're talking about the continuation monad, or you're talking about the state monad, or you're talking about sets as monads. It's exactly the same law.
Yeah, that sounds really interesting.
And that would allow you to go
new category better.
That would allow you to go kind of in a step-by-step fashion from the kind of functional mathematical definition to something that's a little bit more programmatically efficient, and then from there, in this kind of
So my strategy has been to make like very very slow, gradual changes. I mean, we have like a really clean commit history where every change is like super clean, like, and it's like small, and then I have taken great care to make sure that I'm not doing a different computation through this process.
Mm-hmm.
One thing that I have mentioned that's kind of significant is that I did I did end up changing the bet data structure a little bit. So I made the justifications instead of sets, maps from, or like dictionaries from validator to bets observed from those validators.
Yeah. It's a totally natural thing to do.
It's makes some things more efficient. Like if you know what validator, like you know you're looking for a particular validator, so you don't have to go through these sets. You can just kind of go through that path in the dictionaries. It's like much more efficient.
Cool.
The other thing that I did was I added a sequence number to the bet, where basically, if you're, the sequence number has to be like one more than the previous bet by that validator in the justification for it to be valid. And basically, the sequence number is used in order to bound the overhead on checking for equivocation and also checking if a bet is after another. So like, kind of, if I get two bets and I just like see their pre-hashes and I don't have a sequence number, I'm gonna have a worst case of how many times I'm gonna have to resolve this like hash lookup. And so by looking at the sequence numbers, I know basically which one to start at and how many steps to go before being like, oh my God, this guy's Byzantine.
So you've gone back and forth on whether or not to have sequence numbers. I think it's a perfectly
basically I really like the simplicity of the kind of sets no sequence models approach. And this to me is okay because basically what it's doing is it's helping the validator set up a calculation that the adversary needs to do. It's basically like there's like the world of protocol messages, and then there's like the world of like stuff that has epistemic value to the validator, and there's like this transformation that takes place. And basically the sequence numbers just make that easier.
Yes, I agree.
Yeah. So basically I'm starting to like, kind of be comfortable, like, making the mathematical model of the protocol a little more complicated, basically because I'm, doing it in order to produce data structures that's like exactly the same as I was doing before, namely like the information that's given to the ideal adversary.
Yeah, understood.
So I would like to just like share a little like the thing running with like a screen share. Not sure if that's something people would like.
I'd love it.
Okay. But maybe if someone else has an update, now's a good time while I get set up.
Yoichi, any updates?
I was attending a conference in Malta last week. It was a mixture of, Vlad was there too. It was a mixture of crypto people, Bitcoiners, and some Ethereum classic people. I met some people who are designing languages for smart contracts or Bitcoin signatures, and some people sent me papers, and now I'm reading them and making comments. I also met some interactive theorem proving people trying to build a verified compiler from some smart contract language into Ethereum virtual machine. So there is a possibility of collaboration with them.
Cool. Do you want to start your share, or should I?
Go ahead. I have it ready, but go ahead.
Okay, sure. So most of a lot of it was the optimizations that Vlad thoroughly went through. The only other thing is I'm also adding Vitalik's for choice rule to and like simple Casper integration into the Pytherium client, so that will kind of serve as one for further testing and also as like a reference implementation. So that is currently in progress and hopefully will be done in the next couple days.
Cool.
That's it.
Oh, one
Okay,
other
so,
thing. Oh, you ready, Bud?
Go ahead. No,
I was
go
just
ahead.
I was just going to say, Mike and I, we needed this technical result to simplify some of the ladle stuff, and we actually came up with two solutions. And I just published these. We just submitted to Calco 2017 the other solution. So we submitted the first one to MFPS and the second one to Calco. Funnily, both conferences are co-located this year in Slovenia. And I just posted a link to the other solution. And it's kind of cool because it's the first time, to the best of my knowledge, it's the first time ever that someone has given combinators for concurrent calculus that are variable free. And that are provably as expressive as the pi calculus and other things. So
Variable free meaning that they don't have names?
Yeah, there's no names. There's no free bound names anywhere. Mike discovered yesterday that there are, for the second solution, there are some intriguing subsequent results that have to do with normal forms and things like that. It's kind of a little far from Casper, but it is interesting from the point of view of realizing computation. It's like when you think about physical systems, even circuit systems, it's hard to, you don't see variables naturally. Variables aren't really there naturally. You have to do compilation techniques to get it down to physical systems. So these combinators give us, sort of a broader range of potential physical interpretations of computational systems that support concurrency. So that's another interesting implication there.
Yeah, sounds interesting. Cool. Great. So I'm going to share screen.
Please.
So I'm gonna do five validators so they kind of show what's up, and then we'll do more later. So firstly, let me demonstrate some of the functionality that we have. So if every message, so I'm displaying the weights of the validators as the areas of the circles, just kind of a random number with a lower bound right now. It's normally distributed, so there's not actually that much variance between them. Basically what I'm going to show is how we can do like kind of traditional round-based consensus in like the normal number of rounds. So like all these bets are kind of majority estimates in the bets and the justification. And then the nodes are colored green if the adversary failed to attack the view in the justification. And so basically these green ones are safe bets. We also have it working with in kind of a blockchain rather than rounds. This is a kind of not a great simulation, but you see that basically safety happens a lot faster. And I have an off by one bug. This is like one of the outstanding issues right now. This validator doesn't seem to be aware of his own bet, this first one, because I initialized it in a different way than I did with the other round thing. But basically, in a blockchain, there's much more efficient number of messages for safety. And the thing that's kind of, these arrows are really showing the justification dictionary. This is pointing to the last bets from everyone that they know about. Doesn't actually correspond to the message flow. The message flow actually was like this. So this kind of makes the representation kind of a little less pretty. But it turns out that like calculating, making the justifications redundancy free is is a little bit inefficient with the algorithm I was using before, so I kind of just like scrapped it now because redundancy freeness doesn't actually affect safety, but it will optimize network latency. No, sorry, network overhead. And so it's something I plan to add back in, but I haven't thought of an efficient algorithm for it yet. But I'm pretty sure that it'll happen. And then the thing that's cool about this is basically that if we can make here I'm making 95% of the messages fail. And I'm going to end up getting like a kind of oh, sorry, it's still this is a blockchain version. We're going to get like a kind of interesting graph that is not really typical of extensive protocol. We can actually deal with like arbitrary graphs, but only some graphs have consensus basically based on whether the adversary fails at these endpoints. And then this kind of maybe you can observe how much faster it was than the last time, but there's a bottleneck. There was like a bunch of bottlenecks in this code initially. So like now we can run like a relatively decent number of validators pretty quickly. So this is 50 validators, and this is all kind of on one one thread on my laptop here. And basically there's like a slight glitch in the speed between every round, basically during the mem copies. So it seems like they're settling on 0. And then what's going to happen in a few rounds is that they will have safety, or some of them will start to have safety. And basically, as soon as some of them have safety, it ends up spreading really fast, because anyone who observes a safe bet is basically inherits that level of safety. And basically, technically, there's no guarantee that it'll converge, but we've never found that it didn't. If I had enough time to run it, basically. But I'm also not using the most adversarial possible network structure. But you can kind of oh no, what did I do? Oh, it's okay. You kind of see maybe that it's running a lot faster than before. Basically, the mem copy is the main bottleneck now. Still no safety. How disappointing! But it'll happen. Oh, here we go. There it is. Oh baby. So this is 50 validators. And actually, in this example, all of these validators independently realized that they were safe, which is quite interesting that so many of them did that at the same time. And now basically next round, maybe 2 rounds. There was one unsafe one there. Everyone will basically know 1, 2. So yeah, we're missing 2 validators in that last round. So this is 50 validators coming to consensus relatively quickly. I mean, if it wasn't for the mem copy thing, I think it would have been faster. And again, like every round, 95% of the messages are failing, which is kind of interesting, I think, also, because rather than wait and restart or wait until we have reached certain thresholds on a certain index, we just kind of keep rolling this all up together. Until basically until there is consensus. And basically the nice thing about it is that actually there is no there isn't any increase in overhead as in the rounds go, in theory. Basically, there's more overhead if you want to validate all the bets that were ever made, but in terms of the overhead for a validator over time, it doesn't increase. So that's basically all I have to share.
Cool. This is exciting. I'm really looking forward to looking at the Python code and seeing if I can trace it back to the definitions.
Great.
Yeah.
Yeah. I think basically we're just gonna do some refactoring and commenting. Maybe change some variable names and then I'll publish it.
Cool. Yeah, I mean, I think it, the most important thing is to, be able to make a connection between what we believe has been proved correct and the code.
Yeah, agreed. And I've tried my best to make absolutely certain at every step of the way that connection was maintained. At first, it was very easy because I was just implementing the definitions. But
right.
Then,
Yeah, exactly. Exactly. It's that trick of tracing. This program transformation, under all circumstances, will preserve the semantics of the previous program.
Yeah, that's exactly what we're going for. Yep.
Yeah. Right. Yeah.
Unfortunately, sometimes we introduce bugs, but
yeah, well, that's just
but
there are bugs in definitions too, right?
Yeah.
That's why we have automated theorem proving. Absolutely. No, this is great. This is really awesome. I'm very excited. Cool.
Anyone else have anything to share? Cool. Well, I'd be happy to call it quits. I'm not sure about you.
No, I'm all good. I think I'm all for yielding back time as soon as possible.
Cool. Yeah. So I think this was a fun stand-up.
Yes. We're getting there, one step at a time. It's very exciting. Yeah. Cool.
Great.
All right, guys.
Sweet.
I'll see you guys next week.
Awesome.
Cool. See ya.
Greg, if you have time to stay on for like a few minutes, if that's possible.
Yeah, sure. Sounds good.